Hello.
Hello.
Okay, let's begin our seminar. And today it's my pleasure to introduce Professor Hoang from Texas Technical University. Professor Hoang belongs to the scientific school of well-known mathematician Cyprian Foyash, and he has a significant contribution in the theory of nonlinear flows in porous media. And today he will talk about asymptotic expansions for Navier-Stokes equations. Please.
Okay, thank you very much. First of all, I would like to thank the organizers for the invitation and for the arrangement of the talk. It was a surprise because I only met some of you a few times back here in Texas Tech. Well, a long time ago, I guess. So today I will give a talk about the theory of asymptotic expansions for solutions of the Navier-Stokes equations. So this paper now is online with the Journal of Mathematical Analysis and Applications. So the word complicated here, I think I borrowed it from some papers by Alexander Bruno. But I use this here not as a terminology, just as a common term, because what is the level of complication? We don't. So after this one, we can have more complicated expansion. So I don't know. I don't have the definition of complicated expansion. Just a common term. So the outline is I will have an introduction of the theory. So I will briefly say about the case that we can do quickly with exponentially decaying forces. And then I will introduce the form of expansion of our interest in this talk. So one of the technique is the complexification. I will do that. And then some technical details. Now some technical steps for linearized Navier-Stokes and then the main results. So finally, I will have some examples. So first, the introduction. So of course, many of you know the Navier-Stokes equation, which describe the incompressible fluid dynamics. We are considering in the R3 case, and U here is the velocity field, vector field. Nu is the positive viscosity, P is the pressure, and F is the outer body force. So we study the initial value problem, right? And then, so from the tradition of dynamical systems, so we introduce, we denote the ut as a function of T with values in functional spaces, the same with Ft. So in our talk, the notation is that N is a set of natural numbers starting from 1 and Z plus is just non-negative integers. So the motivation of the theory is the result by Foyash back in the 1980s when F, the outer body force, is of the potential form. Then any non-trivial regular solution ut in the case of bounded or periodic domain admits asymptotic expansion of the form like this. So it's the sum of the polynomial in T times the exponential decay also in T. So Qt here has value in some Sobolev spaces. Right, so what does that mean? It means that whenever you have the remainder ut minus the finite sum from 0 to n, for mu n here is increasing to infinity. And then the remainder will have the estimate in Sobolev norms decays faster than the last decaying rate in the approximation. Okay, so that's a starting point. So in fact, that this result is then extended to the Sobolev algebraic species by myself and Martinez in 2017. Sorry. So what does that mean? So it's very similar. So if F has itself as an asymptotic expansion of the similar form, right? Then the solution of Navier-Stokes equations, in this case, it exists for large time. Regular solution exists for large time. Of course, weak solution exists for all time, but because we consider the asymptotic behavior, so asymptotic behavior UT will go to 0. So we have the regular solution for large time, and the regular solution for large time here also have a similar expansion. So the expansion, the theory also extended to more general form, not only the exponential function, but also the other general function decaying rate, psi t. And then we prove that similarly, if the outer body force has the asymptotic expansion of the form when phi and here is independent of time, then all the Lery-Hopf weak solutions also admit a similar solution. So what is the philosophy here? So in fact that we can do this for a very general form of the outer body forces. So the thing is that we have the P decaying rate, psi t to the mu n, when mu n again is positive and go to infinity, and psi t of course go to infinity. And then we have the coefficient, but its coefficient here now is maybe a very complicated function in t, but it will not affect the main decaying rate of psi t to the power mu n. Okay, so and then we hope that, so with outer body forces are of this form, and then any Lery-Hopf weak solution also had a similar asymptotic expansion.
What do you mean it will not affect of decay?
For example, ln(t) times t to the minus mu, right? Mm-hmm. So this one, the key decaying rate, and this one doesn't affect, doesn't add to the, it will not add to this, right? Mm-hmm. So it doesn't affect the main decaying rate of t to the negative mu. So that's
but do we have any qualified estimate for, or we will later will hear you?
Yes, later on we will have, but of course we have the estimate for the rate, but we don't have the estimate for the constants because estimate is very complicated. We cannot, as in PDA, you know, we cannot track all the constants.
Sorry, thank you very much. Thank you.
Thank you for the question. So that's the main goal, and then how much we can extend the class of both psi t and then phi nt, and then of course that's the ongoing research. And then I can say here that all these things that I can do for ODE theory as well. And then of course ODE theory we can do with a very nonlinear systems. So functional setting of Navier-Stokes equation here, I only consider the case of the periodic boundary condition. So take the box with the 3 sides, L1, L2, and L3. I should consider solution which is periodic in each direction with the periodicity Lj. Okay. And for simplicity, and then we assume that solution has 0 average over omega in this sense. And then by scaling the spatial and time variable, we can assume that L star, okay, L star, where is L star? L star is the maximum of all L, and nu is 1. So the point is that then, so that you have the lambda 1, the first eigenvalue of the Stokes operator is 1. So that's the assumption for this one, for the L star equal 2 pi. And then, well, this is the standard setting for people working on Navier-Stokes in the periodic domain. So let script V be the set of omega periodic trigonometric polynomial vector fields with divergent free and 0 average over omega. Then we define the phase space H, and then the space V to be the closure of script V in L2 and then in H1. And then we use the notation is that the single bar is for L2 and double bar is for V. Okay. And then the Stokes operator acting on the domain, which is V intersection with H2, is this. So because this is the periodic case, then in fact that the Stokes operator is just only minus Laplacian. For U is in dA. Okay. And then this Stokes operator has complete orthogonal basis in H and eigenvectors, eigenvalue, positive eigenvalues, which we arrange in the increasing order. Okay. And we denote the spectrum of the Stokes operator is just sigma A. So I just introduce the notation because later on the definitions are very complicated. So, and then we rescale the wave vector, and then the Fourier formulation. So we have the fractional operator a to the power alpha, and then this one is related to algebraic classes when we have e to the sigma ak here, because here we have the a to the power 1/2. So here we have sigma k, the magnitude of k. Okay, and then the algebraic superlap spaces are defined as the domain of the operator a to the power of alpha e to the sigma a 1/2, with the norm is defined as such. So you can see that because of this one, whenever is finite, the norm is finite, it means that the Fourier coefficient of U decays very fast in K, okay, exponentially fast in K. So it makes that the function U here is very, very regular. In fact, that is analytic in spatial variable. And then each Hilbert space here is in fact each space algebraic space G's alpha sigma is really a Hilbert space. Okay, and then the intersection of all is defined by E sigma, infinity sigma. And then the nonlinear term is defined as a BUV is the Leray projection of U dot grad V. Now, the key, the convenient estimate for the norm of the bilinear term here is that if we have alpha greater or equal to 1/2, remember alpha is the power of a to the power alpha. So it's more like this is greater or equal to the H1 here. Then we have the algebraic norm of BUV is bounded by the product of the norm of U and V. But because this is Navier-Stokes, we have to sacrifice a little bit here, right? So we have to estimate BUV in the alpha norm by U to the alpha plus 1/2 V1 alpha plus 1/2. Of course, this is the symmetric form of inequality. I use this for convenience. There are sharper estimates when the estimates are not symmetric, but for this talk, purpose of the paper, for simplicity, I don't want to track the norms in all directions in U and V, so I use this symmetric form. And we assume that, so in fact that the function f is bounded in time, okay, in time and h variable. So it means the L2 norm is bounded in time. Of course, this one is to make sure that the weak formulation of Navier-Stokes makes sense. But later on, because f go to 0 to infinity, so we have stronger assumption. And in that case, that we can rewrite the Navier-Stokes equation in the functional form. So we consider quickly first that the case when the forces decay exponentially. So in this case, that we introduce, this is not the main point of the talk, but I want to review that what we can do previously. So we say that the function is the S polynomial if it is the polynomial and times the sine or cosine. Of course, some of you may recognize that exactly that this is that you have the polynomial times the exponential with the imaginary power, right? Then an asymptotic expansion in this case is very similar to Fourier-Short result. So if the function g for large time has an asymptotic expansion, e to the minus gamma t times p here is the S polynomial. It depends, either we can use the S polynomial or just polynomial, but in general that we use the S polynomial, it means that you have the sinusoidal functions. And then, so the expansion means that the remainder by its finite approximation decays faster than the exponential, the last exponential term in the sum, in the approximation. So the theorem is that then I skip the details. If I have the outer body force has an asymptotic expansion, okay, in P, in E here. So E sigma infinity is remember, is the intersection of the G alpha sigma for all alpha positive. So this requires the expansion holds for all Sobolev spaces. If you consider the algebraic space and then the algebraic class is fixed, but the all Sobolev norms, it holds for all Sobolev norms, okay? Then any Lorentz weak solution has a similar asymptotic expansion, again, for all Sobolev spaces. Yeah. So it requires very strongly that the body force has the expansion for all Sobolev spaces. And then we will see that, and then the expansion really depends on each individual solution U. So okay. So we will compare these properties of the expansion with our later expansion. So this theory can be done more or less exactly like the original proof by Fourier and Shaw. So I did it a couple of times with the Martinez and also with the paper with Adris TT on the rotating Navier-Stokes equations. So I will not present it here. And then in fact that if you rewrite like UT is about like sum of UNT, and then F is about like sum of FNT, then in fact that we have a very nice linearization of the Navier-Stokes equations. So you have the linear, in fact that you have only the linear equation, and the bound nonlinear term come from the previous terms. So in fact that you can consider this as a linearization of Navier-Stokes equation, and of course then, and in this case that we have if when f equals 0, and then you have the theory of Poincaré Dulac normal form. for Navier-Stokes equation. That's the work by Fourier and Sort originally, and then later on with me. So now we move to the main part of the talk. So when we say the complicated asymptotic expansion, so we focus more on the power and we have the power function and logarithmic function and iterated logarithmic function. But not only in T, but in other, okay? And then you have the sine and cosine, okay? But sine and cosine not only in T, but also in the log and iterated log. So it's very complicated. So we will have to use the complex functions, but not too much, because we don't use the multi-valued complex function. We just use the complex function with the real base. So we don't use a multi-valued complex function. Okay. So we use the standard one. And then the notation is that you have the exponential function and the iterated exponential function. We have the power function. Now, for the sake of unification of the notation, we use L-1 as exponential, and L0 is T, and then the other standard one is that LNT and iterated LN logarithmic function. So for example, and then I denote that the script L hat is a function starting from exponential and then T and LMT and iterated logarithmic functions. Okay. Now, of course, you have all kinds of the properties when you compare the iterated logarithmic function, and then you have the derivative. So because of the chain rule, the derivative always produce 1 over T here, and then this will give us estimate of the terms later. So I will quickly say that we use many times this very simple but convenient estimate of the integral, because it appears many times. For example, when we solve the linear system and we have the variation of constant formula and the forcing term has this rate of decaying, and then we have to estimate. And it turns out that for M is in here, so it means that either you have this is a power or iterated logarithmic functions, and then we can always estimate this one when last time by the function itself. Now for Z, remember this is a vector. So later on we will apply to e to the t, and then L and T, so on and so forth. And then we have the power with the possible complex power, right? And then we have Z to the power alpha is standard notation is here. But remember that this one we can write that later on you may have L and T to the power alpha J, right? Of alpha 1. And then this can write as the sine and cosine of L and T. Now the class here, the set of indices is here that at the level of later on LMT. So before that, we had the real part, okay, is 0. At this level, we had the real part is mu, and after that, we don't care. Yeah, after that, we don't care. Good. And then we have the easy estimate, because if alpha belong to this, so because of this picture, of course, the first big decaying rate or growth rate is Lm to the power Lmt. So if we increase here a little bit, of course, this is 0 limit. So our function will be like this. So the Pz will be z to the alpha psi alpha. So the finite sum. Now, of course, we need to put structure on that. And though the structure in that is that all the alpha here belong to the set here. So again, it means that the first kind of rate, either growth rate, is that Lmt to the power mu. Okay, so that's the key thing. So before that, all we have only sine or cosine, and after that, we don't care. Okay, so the definition of our asymptotic expansion is that we have the class of function with the decaying rate, remember, so, and then the logarithmic function or power function is indexed by m star. So later on, the mean decaying rate will be like this. Okay, and then, so we have this kind of asymptotic expansion. If you have the remainder, when you have the finite sum of approximation, then it decays faster, Lm star t to the power negative mu for mu greater than the last power in the sum. So that's this is the extension of the Fourier idea. Okay. Good. So for example, m star equals 0, and then we have the power form of the expansion. So and then I call it the term that this is the coherent decay. If the function has this kind of form, and then we have the coherent power or logarithmic or iterated logarithmic decay. So because our calculations, we need because we introduce the complex function with the complex power, so we have to genuinely work with the complex spaces and operators. So I present here the complexification of real linear spaces, because the Navier-Stokes equation originally is for real valued functions. So all the Sobolev spaces and algebraic spaces are for real value functions. So now we have to complexify the spaces. So this technique will complexify the spaces, but some other techniques, for example, when we study the analyticity in time, like Fourier and Tillman did, and then they complexify also the time, but we don't complexify the time. We only complexify the spaces. So we define the complexification of the real linear space naturally by this, right? But when we want to introduce a norm for the complexified spaces, and then we have to work with the inner product. So if it is the real inner product, and then the XC will become the complex inner product with the natural definition, just by expansion of the kind of expansion of the inner product. And then the norm is very naturally defined by this, right? So for the linear operator, if you start with L from X to Y, real spaces, and then you can define naturally the complexification like this, right? Then we can easily check that just like a real matrix is considered as a complex matrix. So in the case of the Rn, finite dimensional space is easy, but we will work with infinite dimensional spaces, so we have to be a little bit more careful. But everything works, so it will not change the norm, okay, the norm of the linear operator. And now we do the specific complexification for the Navier-Stokes equation. Let me pause a little bit. Anybody has any questions? Okay.
No, I'm listening very carefully.
Okay, thank you.
Thank you very much. I will ask on the end.
Okay, so the complexification, so we have the G alpha sigma is a Zevray Sobolev space. And when we do complexification, it denote like this. And then all the norms for the complexified species, now we use the old notation, okay? So we don't want to create so many notations. So we use the old notation for the norm. But for the space, we write it very carefully, the complexification. And then the Stokes operator, here we consider just from DA to H, okay? We don't do the more general one. So we do from DA to H, and then the complexification, remember this one. So remember that D of A, right, E0, A1/2. So it's exactly the DA. Okay. So again, we define very naturally. And then the same with the nonlinear term. So everything is defined naturally. And then in the complex, in the Fourier formulation, so in HC, and then we write like this. But even we write like this, we never combine we do not combine the Fourier coefficient of U and IV. So we always rewrite as the pair of expansion Fourier series plus I times a Fourier series. And then we define naturally again AC alpha, okay, to the power alpha like this. And the exponential also with A1/2 here is less the same. And then we can easily check these properties. Again, these are very formal, but it's very natural, like I said, a matrix or exponential function of the real matrix. We consider as the complex matrix, that's all. Now one of the first natural estimates for this is that if we have AC plus I omega, remember AC here is more like real, even we do the complexification, but A we start at the real, like the real operator. So that's why when we plus I omega, so the inverse of course exists. And then the main, so we can say that the main contribution in the norm estimate in fact come from A. So that's why when we do the inverse, even with plus I omega, we can still get back to just. So this is that we do the alpha plus 1. But remember, A here is the Stokes operator. So plus 1 in the Stokes operator to the power 1. So, but we do the inverse. So we get back to just the norm alpha. So these things, of course, are obvious for finite dimensional space, but for infinite dimensional space, we need a little bit more careful. And then again, we have to think of AC as...
Can you remind us a little bit, for me at least, what is G alpha?
What is what, Akif?
G alpha, G alpha.
G?
G alpha sigma C. What is this class?
So the
mapping
U
from
of alpha sigma is A to the alpha, E to the sigma, A1/2 U.
Mm-hmm.
Okay.
Thank you. Thank you.
So and then each of them here you can put the KL to the 2 alpha.
Mm-hmm.
Okay. So when you see A, you put the KL square when you do the Fourier formulation. Thank you. Mm-hmm. And then the same here, you can see the AC as real. So when you do the conjugate, okay, of course the conjugate is defined similarly for the complexified species, and then you can do naturally. So of course, I will not focus on this one. I just say that because that AC here can be thought as a real operator, even is a complexified version, and then but it acts like a a real operator. So all the conjugation works nicely. And then the complexified version of the bilinear term is bounded very naturally. Okay, still not there yet. So now this one introduce the new operator, the key new operator, so that we can do the approximation. So if you have a function like this, okay, so it's in this class, it means that beta real of alpha negative 1 is 0, right? And then we define ZAC is the same, but we apply this. And this makes sense because the real part of alpha negative 1 is 0. So it is imaginary. So we can do that. We just have the theorem before. Okay. And with that one, so we will have that ZA map. So because of we have the negative 1 here, so we will gain the regularity of the functions. Okay. And more generally, okay, so we have this in mu alpha and then mu G alpha plus 1. So we will gain one order of the, not of the derivative, two order of derivative for the function. So one order of the Stokes operator, two orders of derivative. So approximation for the solution of the linearized Navier-Stokes. So the key thing is that then we do the linearization of the Navier-Stokes equation. So this is the equation.
Hoang, one moment.
Yes, sir.
Please higher and higher.
Yeah.
More higher.
Yeah. Yes.
More. Okay. Wow.
Yeah.
Так.
Подожди, давай, тогда опусти еще.
A bit below.
Oh.
Yeah.
What moment? Why is this IC minus omega plus equal conjugate?
Okay. Or conjugate here?
Right.
Conjugate here?
I think here conjugate, да, окей, хорошо, окей.
Yes.
Okay. Все, Юр? Понял?
Все.
Yeah, because I see here acting like a real operator. So everything works.
Yes. Okay. Yeah, thank you.
This one, I say this, but I will not use it in this talk, but it is part of the proof, because when we do the complexification and then we calculate everything complex, but we have to make sure that the result, in fact, when we get back is real in all the approximations. So we have to check carefully that, and then we will use that property, conjugation property, when we check that everything, when we do actually give you the real result, not the complex result. Because we still deal with the Navier-Stokes equation, which is the real valued function. Okay, so now we consider one of the key steps, okay, of the approximation is that we consider the linearized Navier-Stokes equation. So we have the linear part, the main part with the specific decaying rate and the form of the function, and the perturbation which decays faster. So this is decay faster than P. Okay. Yeah. And then the P here, remember the P here in this class, and then we either have the power or iterated or log or iterated log. Okay. So this is the key difference from the case when P here is exponential. So the main thing is that then first we have, of course, we have the regularity. So we gain a little bit. Remember here we have the forcing term depends on time. So if we have the full two derivative, gain two derivative, and then we have to do the conditions on the standard one, we'll have the condition on the time derivative. But because that I will not use any time derivative conditions, so at least that up to now I can only gain the regularity, but I have to sacrifice a little bit. Okay. Good. Because I don't assume anything about a time derivative, which usually the standard regularity theory uses. And then in this case, then I can approximate any solution W here by exactly the operator ZAC, okay, with a little bit, we still get a lot of regularity here, but not the optimal one. I don't know if we can have the optimal, but let's say that I cannot have the optimal one. And the decaying rate here is mu to the minus delta star. Remember, mu, original mu here comes from P. P has the rate of negative mu, and then the remainder here has a rate decaying faster than that. Okay, so that's the main thing. I don't think that I have time to present the proof, so I'm sorry that I will skip it. I prepared a lot, but
Vlad, excuse me. This delta star, does it depend on mu?
Yes, in general, the delta star, yes, depends on mu.
Mm-hmm. Okay.
In the proof, I have more explicit delta star, but let's say that we don't want to make it too short, so I say that it depends on mu.
Depends on mu. Okay, okay, thank you.
Yeah, but I think that we can do a little bit more specific than that. So if we go through the proof, then I think that we can point out, but let's see. Okay, now is the main result. So first that we will put away that the existence and the asymptotic estimates. Okay, so if the boundary force decays as Lm to the power negative mu, then the lower half, a weak solution of Navier-Stokes equation, okay, because this one, it goes down to zero. So for a long time, the U will be also small, but when it is small, and then it will become regular because I start with the space with at least in V, it means that you have that in H1. So when time is large, U is small in H1. And then when U is small in H1, we have the theory that the solution is unique from there. So from there, last time, and then we have solution is regular, and then we can estimate. Okay, and again here, in fact, that we can gain almost optimal. So we have that we gain almost two derivatives. Yes,
and this T hat depend on initial data. On what is T hat?
Oh, it depends on solution. T star, you mean T hat?
Yeah, T hat.
Because you have, remember, you have to do the bootstrapping so many steps. The first step, right? The first step, like from A to V, and then we can use the energy inequality to estimate T hat, okay? Mm-hmm. But after that, from V, and then you do more, and from to the A, and then from the A, you do more and more, right? Mm-hmm. And then I lose track. Mm-hmm. Okay, I lose track. So it depends on UT, because Larry Half equation may not be unique. We don't know. So in fact, U star doesn't even depend on initial data. It depends on solution. Okay, right?
So it means that for fixed solution, your t hat
Yeah.
will different depending
Yes.
on.
Yes. Even if you start with the same initial data, because I work with the general weak solution, and then general weak solution, we don't know if it's unique. So T star depends on the solution, but solution later on becomes regular and then it decays. So it depends on solution. Yes. Thank you.
In a sense, we don't have stability.
Stability of what?
Of t hat with respect to.
Yeah, we don't know, of course. We don't know. Yeah. Yeah.
Possibility.
Because maybe that the weak solution, maybe it can be here, but it can be like this. So we don't know, right? So we don't know what T star.
Thank you.
Okay, so again, we can track, but extremely hard. Yeah. Okay. Now I introduce more operator. So the MJ operator, more or less, when you take the derivative. So you multiply by alpha j. And RP here is a combination of all those MJ. Okay, but remember that we have here. Later on, it will produce 1 over T. Okay. Now, another way to introduce RP is like by the standard derivative. But anyway. Then if Q is a function in the class of our interest, and then we can always, when you take the time derivative, it produces that M minus 1Q plus RQ. Okay. And then this, because remember that RQ give you like 1 over T. When and then when you do the approximation between the derivative and M minus here, and then you can estimate the remainder. Yeah. Now, still not there yet. So because again, we do with the real linear space value function. So when we have this kind of function, to make sure that everything gives you the real value functions, and then you need the conjugacy condition. That's all. Okay, so this makes to make sure that we have the real valued function. And then this lemma said that if you have real value function, all the operator from real value function will map to the real value function. Okay, and then we continue to keep the for example here, if R map here, and then if you consider the T to the power, so remember R here, we always produce 1 over T, so we always gain a little bit. We gain the power in time. Okay, will be mu minus 1. So everything just works out naturally. And then everything also works with the same with this operator. So when it becomes real value functions, and then everything works. And again, here we still gain the regularity. Okay. Now we study with the force has the power decay. So it means that suppose that the force has the asymptotic expansion of this form. Remember that M star here, power decays, and then more or less that you have some P hat N times that then T to the power minus mu. Okay. Yes, sir.
But when you introduce expansion like FT minus portion of summation until n capital less than equal, what is definition of this expansion?
Similar, the same.
The same. Mm-hmm.
Yeah, it means what? The F minus the sum from 1 to n is O. Expansion when T go to infinity, right? Of L of T to the minus mu n.
So thank you, I understood.
Yeah. And then this is in this is only in one fixed space, Not for all the Sobolev spaces, one fixed space. Yes. Good. Good, Akif.
Yeah, understood. Thank you.
Thanks. Now, and then we define the terms of approximation.
One moment. I
Yes.
saw
Yes, sir.
in your previously results that you have minus epsilon.
Here.
What is the epsilon? It is.
Oh, you mean this one?
No.
No, high.
Так, Юр, epsilon was arbitrarily small.
Значит, логарифм, что ли, я так понимаю?
Ну, что-то типа того, да.
Where epsilon?
Earlier you had the result not completely sharp with.
Oh, okay, wait. I will say on that. This is the definition.
Yes.
This is the assumption on here. We are talking about the force, not yet the solution. What you say is about solution. We will go on that.
Yes.
Okay.
I explained what was that epsilon. It was arbitrarily small.
Any later on, any epsilon between 0 and 1, any. Of course, we will take it as small as possible, but in general, it's any.
Okay.
But of course, we want to take it as most close to epsilon 0.
Thank you very much. Хорошо, спасибо.
Thank you. So, so the term of approximation later on we will do is that then Qn is the ZAC of Pn minus the first term come from the previous term Qm, Qj. Because of this condition, everything is positive. So, and then strictly increasing. So this is from the previous terms. And this term comes from the time derivative. Okay, so come from time derivative because here we are talking about the power expansion. So when you take the time derivative, we produce -1, right? Power -1. So we have to take from the previous one, So it becomes that RQ lambda when mu lambda plus 1 is mu n. So all these things that you can try to, I think you can do it by take the expansion and do the substitution and do the equate the coefficients. But the definition is this complicated. But you can guess the form, of course, when you do, when we try to find the formulation of the theorem, you can just check the expansion, do substitution and find out, right? Now, yes, this is what you're asking for. Remember the definition of Qn here is independent of a solution. So, but any Larry-Hopwick solution, okay, good. So we can do approximation here, and your epsilon here, now I change to rho, okay, sorry. I change to rho here. So we will have that the estimate in the norm alpha plus 1 minus rho. Again, I don't have the optimal norm estimate here. Okay, decays again faster than the last term in the sum. Okay, so does it answer your question now?
Excellent.
And then any rho from 0, 1.
Excellent.
Okay. Now, so if you want, you can say that any Larry-Hopwick solution has an asymptotic expansion in any of the space here. And I don't have the optimal one. Good. Now, even we only have the expansion with not optimal, but each term Qn here, in fact, belong to the optimal spaces. Here. So in fact, that each term belongs to the optimal space, but then the error estimate is not optimal. So it's a little bit, very tiny gap there, but I cannot overcome it because remember, I don't impose any conditions on the time derivative. I think we have time. So you give me 15 minutes, right?
Oh, no, you can continue.
Yeah, okay. So, okay, I think that, yeah, so again, I just give very quick sketch of the proof and other technical details that I don't think that I can go into detail. Yeah. So we prove by induction. So the first step, of course, you have to do the first step, but okay, I skip that. Okay. So the first step, I skip that coming from the asymptotic estimate. So the first step, in fact, is easy. So I do the induction step when we already have the term, the approximate term, and then you do the error, the remainder. Now, you define, of course, and then you do usually what? You do substitution into the, so U equal the sum, right? Plus the V and T, and then you do substitution into Navier-Stokes equation. Remember Navier-Stokes equation, in this case that we have the form UT plus AU plus BUU equals F, right? And now AU, BUU here, now we can make it the complexified form. So then we have QG here is in fact that the one of the main term when you do the sum, right? When you have the sum, when you plug in, you have the main term here. And remember QM, QJ here are real, but I do this complexified. Then we will find out that Vn prime plus AVN equals Pn. Pn here come from F. Qn here come from the bilinear term, and chi n here comes from the time derivative, right? Plus the perturbation. Now, of course, there are many steps here I skipped because then you can see that there are many things in between. So because this one, I only pick up some rate, right? But there are many rates in between that it will be vanished. It will be canceled because of the way we construct the QZM. They will cancel out, but I do not present here. Okay. So this term here, remember this one is the good part because we have the structure and we can check that this one, in fact, belong to the right class with the right rate of decay and also has real value. Okay. And this is the right rate of decay. Okay, and this is give you the regularity. And then the remainder of the noise or the perturbation, in fact, you can check that it decays, okay, faster than the rate in the function which has the structure, okay? So this one has the rate negative mu n plus 1, and the remainder or the perturbation decays faster than that. Okay, so I try right here. In this case, you do this one. Okay, and then we use the linear approximation. Okay, linearized approximation. We do the approximation for linearized Navier-Stokes equation. And then in fact that you have Vn minus ZAC of that function decays, okay, of the rate faster than the one in the approximation. Okay, so remember that this is the next rate. This will give you the next rate. Okay. Oh, why do I change to red? Sorry, I do go back to blue. And then this approximation function, in fact, is by definition is our next approximation we defined from beginning. Okay. Therefore, the Vn minus the approximation decays faster than the last rate. And then this is the remainder from 1 to n. So we have one more term. So this means the remainder of the next approximation from 1 to n plus 1 decays faster than the specified rate we want. And this is true again for any row from 0 to 1.
Luan, I have a question here. Delta, the parameter delta, depends on mu and on solution. Yes. What the next mu n plus 2? Am I right that it is just mu n plus 1 plus delta n plus 1?
Oh, you tell about delta or mu? No, mu is given. Mu n is given in this case.
Well, but
you I skipped that. You're right. You're quite right. Here. You see that? You see that?
So you mu n have prescribed rate of increasing.
Yes, but okay. This one I already prepared it. So if you have for example, you have f is about the sum of, let's say that p hat n t to minus gamma n. So I have to prepare to mu n here by what? I need that mu n plus mu m must be equal to mu k. Because of the bilinear term, right? Bilinear term, you have two rates and then you create another rate by multiplication.
I see.
And then the time derivative is that mu n plus 1 must be another mu k, right?
I
so that's
see.
why they preserve the addition and the unit increment.
Well,
very good explanation. Thank you, Doc.
Yeah, so if you have, thank you. So if you have original gamma and then you insert this one and insert the zero polynomial, zero function, right? When you insert this one, right? To make sure this. So you can generate that and then you prepare.
Уже ход дельта n мы вообще поняли, я не понял. Что ход дельта n?
Дельта n это то, насколько, ну вот...
Ну, явно не указано вообще никак.
Нет. Оно зависит даже от решения.
Вот это уже.
Okay, yeah, let's continue.
So delta n is not too bad. In the paper, I track a little bit delta n. It's not too bad.
So it cannot go to 0.
Delta n?
Yes.
No, because we take we just because there exists one delta n, so we can find out what delta n is. What not find out, but there exists one greater than 0. So when you say it goes 0, when?
When n tends to infinity.
Not necessary. So usually also it you're correct. So because it also this delta n also depends on what? On original delta n here. This also gives you kind of delta original, right? Let's say delta 0 to n. So that delta n depends on this delta n as well.
Okay. Right? So if I have a good estimate of the remainder For the right-hand side, then I will have good estimate of the remainder for the solution. Yeah?
Yes.
Okay,
so as I said, that the only thing that if delta 0 n here is too good, and then, for example, with delta n here, usually I had to check it's from 0 to 1. Okay. So if delta n0 is too good, of course, I cannot take all the good one for delta n0.
Okay.
But I had to cut down a little bit. But more or less, I kind of delta n. Of course, first you have to have less than or equal to delta n0, right? But it's not too bad. So maybe half of delta n0. But you also have to have this one. Because you cannot take the too good delta n0. We cannot take
surely.
Yeah, thank you.
Okay.
So finally, that's it. So the case of the logarithmic or iterated logarithmic is even easier. So we have the expansion here, right? For f. Then here Qn here has no chi k, no chi n. Why? Okay, and then you have that U has expansion like that again in the almost optimal one. Why? Because chi n here comes from the time derivative, and time derivative comes from RQ. But RQ here, remember, RQ always produce 1 over T. But remember here, we consider that M0 here greater or equal to 1.
Yeah. So
it means that LMT here
is lost in the logarithmic scale.
Yes. Yeah, quite correct. So in fact, that this was too fast, too small. So of course, if you consider log or the iterated log, doesn't mean anything. So it means that on all our estimate or our calculation or our algebraic relation, we just check chi k to be 0. And that's it. I don't think I have, okay. So alternative statement is that here even we already impose that all the expansion have real value. But if you really want to say everything is real, right? And then you can impose that all the powers are real, and then whatever not real, you have to express in terms of sine and cosine, right? So the complex power you express as the real power times sine and cosine, and sine and cosine of maybe the logarithmic functions. And with that one, of course, you just do the conversion, right? You can do the conversion that if you have starting from the 1 with the complex power, but you impose the value to be real, okay? And then you can convert to be the one with the real formulation with the, let's say, real functions, okay? And real powers, whatever. But the only tiny thing to be careful is that then, because of this one, remember, so this is, for example, you have a log, jth log, iterated log, and then when you do the sine, cosine, you lose a little bit. You artificially create the next iterated log, logarithmic functions. But you make it more carefully that, in fact, the Q here get back to the same K, okay? If you have the function has the form with the alpha K is real, okay? And then the other way around, if you start with something real, and then this one you don't lose anything, and then you have everything is a real. This is real, again, this is real sine, cosine. Let's say sine, cosine. And then this gives you the complex power, and then this with real value. Right? And then but then kind of when you convert one to the other and the other to the one, you have to make sure that everything, nothing artificial is created. So in fact, that from here, okay, from A to B, and then you have this condition. And remember, this condition, if you go back, and then you can get from B to A, right? So nothing artificially created with the extra logarithmic. And then you say that, okay, with these classes, and then you have, if F has that expansion in that class, and then U has expansion in that class. And I think that's it. And then I have example, but I think it's enough. A lot of, and this one you just work it out. I just write down to see what it is. But I think I stop here. Thank you very much for your attention and all the questions.
Okay, let's thank our speaker. Yeah, please, comments or questions?
I have question. One, if I well understood that right-hand side can oscillate but decay, correct?
Yes, sir. Yes.
Yeah. But it should, and then in this case we have a corresponding estimate for solutions.
Yes.
In appropriate speed. And but what about, you said about optimal estimate? What means optimal? Optimal means, is it achievable or not? What do you think?
I guess that, but you have to find a counter example. I don't think we can get it because we have no condition. Remember, we have no condition on the time derivative. So if you have no condition on the time derivative, and I guess that the best you can say that is almost optimal, but I cannot find example. So maybe some people, remember this is we only do the linear problem. Okay, and then linear problem with the time dependent forces. But I could not find the example right now.
One question, please.
Yes, please.
Давай.
Вот, когда мы там пишем уравнение, вот, Саш, переведи. Вначале там у нас там правая часть, там функция, ну пусть функция какого-то пространства, начальное данное какое-то пространство. Можно написать заранее какую-то асимптотику, знаете функции, какого они класса. Вот, переведи ему на русский.
Да не, сейчас, тут и переводить не надо. Значит, если правая часть имеет асимптотику соответствующую, то тогда получается...
Начальная функция, она какого-нибудь там тоже...
Нет, но начальная функция, она никаких асимптотик не имеет. Она же не
правая
зависит.
часть, да?
Вот, правая часть только. Yeah, okay. The question was whether you can write down the asymptotic for explicitly asymptotic for solution from asymptotic for the right hand side. Yeah, yes, but very in very complicated terms. Sure. Yes. Yeah. Well,
so when I say about complicated, now I can think of the things that are even more complicated.
Yes. Yes. Okay.
Когда правая часть отхода, там можно ведь написать ее разложение в ряд, там, и хреначить, я еще не знаю. Там.
Ну, примерно так и есть.
А что, да, какого класса и считать асимптотику?
Ну, примерно так и есть. Вот здесь говорится об обосновании этого. Это асимптотики.
Если о правой части, там очень было сказано гнилых. В общем, ладно, хорошо, не буду переводить.
Нет, ничего. Так, well, yeah, Lord, please stop sharing.
Oh, okay.
Well, so let's thank the speaker again.
Thank you very much.
Yeah.
So, Ron, I'm sorry, I'm not at home. I cannot talk to you on phone. I will call you tomorrow.
Okay, thank you, Akif.
So it was a big pleasure.